All right, lecture 23 today. I think we have 37 lectures total in the semester, so we're getting close to 2/3 of the way through here. Our third exam, I believe it's November 18th. Is that right? Okay, so that's that's 18 days from now. Today's Halloween. My mom's birthday. Hi, Mom. Happy birthday. And yeah, 2016. I do want to spend still more time in chapter 5, but we are going to start chapter 6 today, so we're going to spend a bunch of time still with integrals and then start on infinite series. And I think one thing that would be good to emphasize is that you can sometimes combine the chain rule with the fundamental theorem of calculus as just a test kind of problem where you are testing, do you understand these ideas and can you put them together? If you look on old exam 3s, you'll often see problems like this. I'll say, define a function capital F by an integral of some trig function, say with the input maybe to the third power or something like that. And just to be different, let me pick something other than 0 for the lower limit of integration, maybe -1 for the lower limit of integration. And I could pick x here, but I'm going to be a little extra tricky here. I'm going to pick cosine of x for that upper limit of the integral. We've seen some completion problems somewhat similar to this theme. This does define a function, a well-defined function for any x. Give me any number x. I first find the cosine of that number x, and then I do the resulting integral. The word do probably should be in quotes, though, because you can't find an antiderivative for this integral. You'd have to numerically approximate it. Okay, but the integral does exist for each value of x, so this defines a function of x whose derivative can be found. That's a little tricky, though. Use the fundamental theorem of calculus, but what else did I say? Use the chain rule. The cosine of x in that upper limit of the integral is the inside function, because when you plug a number in here, you take the cosine first. That's what gets done first. I'll go ahead and write down the answer, and then I'll write the formula for the chain rule and we'll compare. The derivative of the integral is the integrand, replace the t with whatever's up there. In this case, it's not an x, it's a cosine of x. So inside here we get cos cubed x. But then don't forget to multiply times the derivative of the inside function, the derivative of cosine of x being negative sine of x. So that would be the answer right there. Is it really the chain rule? Yeah. Let's see, if you let, little g of x equal the integral from -1 to x of sine of t cubed, and let little h of x be cosine of x, capital F of x is the composition g of h of x. You are plugging h of x into g to get capital F. And the abstract form of the chain rule in this context is that capital F prime would be g prime of h of x times h prime of x being negative sine of x. G prime by the fundamental theorem of calculus of x is sine of x cubed. You've got to plug h of x into that derivative, so you get sine of cos cubed. When you do that, again, times negative sine of x. So if you go ahead and think about it this way, maybe you'd be less likely to make a mistake. And that would be a fine way to do it. I could also ask you, based on this, give me the first positive critical point of f, capital F. The first positive critical point of capital F. It does have a critical point at x equals 0, because sine of 0 is 0. What's the first positive critical point? It would be Well, either where this is equal to pi, sine of pi is 0, or where this is equal to, well, when x equals pi itself, making this 0. Where does cos cubed x first equal pi? When cosine of x first equals the cube root of pi, the first positive value where that's going to happen would be, I guess, the arc cosine of cube root of pi. Oh, although, wait a minute, will that ever happen? That won't happen, will it? Can't happen. So I made an example where that can't happen. Right? Cosine is always between -1 and 1. That can't happen, so I guess you only need to worry about that part. And that's going to be 0. The first positive value of x would be x equals pi. Didn't expect that to happen, that's why I sort of was thrown off guard there. Is this really what's going on? Let's check to see what these graphs look like. Probably it would be best to use n integrate to do the integral, numerical approximation. We're integrating sine of t cubed. T goes from -1 to cosine of x. Again, the -1 is just an arbitrary thing. I could have picked it to be 0 or 2 or 7 or whatever. It doesn't matter what the lower limit of the integral is. Although it does affect what antiderivative you get out of this. By starting at -1, I'm guaranteeing that my antiderivative is going to have an x-intercept at -1. So let's see if Mathematica probably won't know how to differentiate that since I'm doing numerical integration. But let me go ahead and type the answer for the derivative. Negative sine of x times sine of cosine of x quantity cubed. That should be the antiderivative. Let's plot them both. I'll go negative 2 pi to pi, to positive 2 pi. Let's make the original let's make the derivative red and the original function blue. Takes a little bit of time to draw it because it's doing a lot of numerical integrations there. There we go. I guess it wasn't too strange. So the original function there, capital F, that is in blue. Oh, okay. I was a little confused about it. It's not necessarily going to have an x-intercept at -1. Because when x is -1, cosine of -1 is not -1. I was confused there. It would have had an x-intercept at -1 if the upper limit of the integral had been x. But when x is -1, you get cosine of -1. Anyway, the blue graph is the original function, the integral. The red graph is its derivative. Does that make sense? Yeah, where the red graph is 0. Here, 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 here. The blue graph has a horizontal tangent at those points. Where the red graph is positive, the slope of the blue graph is positive. Where the red graph is negative, the slope of the blue graph is negative. And you can try checking the actual values, the actual slopes themselves. Not as strange as I was expecting, but it is an example that works. Okay? So you can expect a problem like this perhaps on exam 3, although I'd probably make it be something where you'd focus on this input being equal to pi. for the first positive critical point. I'd make it so that input could equal pi somewhere.
So at the very beginning, you mentioned that we would need the FTC for this to solve it.
Yep.
Where is that coming?
Right there. Differentiate that function to get this. So it was part of what we did right here, sine of this. We talked last week, I think a week ago, maybe it was even more than a week ago, about how to prove the substitution rule with the fundamental theorem of calculus. You may have forgotten already. It was written in the book like this. Like that. So look back in your notes or look at the old video of when we did that. That could show up on the test. Today I want to do integration by parts. What does the integration by parts formula look like in terms of definite integrals? And again, for sake of time in here, I'm not bothering to write these as theorems. They are written as theorems in the textbook. So there are hypotheses. Integration by parts refers to integrating functions of the form f times g prime for two other functions f and g. Typically in calc books we write those as u and v prime. And the answer for how to rewrite this in a way that is hopefully helpful is to write it like that. In calculus, you'll typically see it either written like this, and I'm writing these as antiderivatives, or perhaps like this. Okay, our calc book typically writes it like this, and we use here. Other calc books write it like this. It's the same thing. Essentially, f is playing the role of u, and g is playing the role of v. These things are functions of some other variable like x. But we are doing this for definite integrals. And as such, that means we want to use the fundamental theorem of calculus to prove this. It's actually easier than the substitution formula to prove. What kinds of assumptions would we be needing? We'd be needing to assume that f times g prime and f prime times g are Riemann integrable. Certainly if we assumed f and g were both differentiable with continuous derivatives, that would be enough. Can we get away with less? They assume f and g are differentiable. Their derivatives are Riemann integrable. They don't assume their derivatives are necessarily continuous, but they do assume they're Riemann integrable. Any ideas what to do here? This would be equivalent to this statement. Does that help? Doesn't help enough? That would be equivalent to this. Yeah, that looks like a product rule. And if f and g are differentiable, this would be the derivative of f times g. So essentially it's the product rule along with the fundamental theorem of calculus. F times g is going to be an antiderivative of this function. Therefore this integral must be this difference. Basically you're done. So that's actually easier than the substitution problem. By the product rule, f and g are differentiable, so f times g prime is this. Because of your assumptions about f prime and g prime being Riemann integrable, these things are going to be Riemann integrable, and their sum will be as well. By the fundamental theorem of calculus, that integral equals this difference because, again, f times g is an antiderivative of the integral. And then it's just rearrangement back to this form. Just some algebra after that one. We are also using linearity to say this integral is the same as the sum of these two integrals. That's the linearity property. Okay, so I think if you look on old exam 3s, not necessarily every exam 3, but on at least one of them probably I'd put either this one or the substitution proof on exam 3. And you should know. You had some problems about average value of the function. Actually, let's just look at the Mathematica. Come over here. Average value of a Riemann integrable function, by definition, is this. V for value, that's the notation the book uses. F bar is my notation, supposed to be reminiscent of X bar in statistics. It's a number, it's not a function. Okay, F bar is not a function, it's a number, it's the average value. Integrate the function and divide by the length of the interval, b minus a. Okay? This has a pretty simple geometric interpretation. The integral, when your function is above the axis, is going to be the area under the graph. If I multiply both sides of this equation by b minus a, I could write the equation as v times b minus a equals the integral. So the area under the graph is the same as v times b minus a. V times b minus a, well, b minus a is the base of the rectangle from over the interval from a to b. V would be the height of a rectangle with the same area. So down here, the red graph is the graph of the function, which happens to be 2x squared minus x cubed. Starting over the interval from 0 to 1. The blue graph is a rectangle whose height is the average value. The area of this rectangle, base times height, is the same as the area under the graph. If I change a and b, for example, increase b, the graph continues up there, so the average value's got to keep going up to make the areas the same. I made this graph so it comes back down to the axis at 2. The area under that graph is the same as the area of this rectangle, where again the height of the rectangle is the average value. The function goes negative now, and so now you need to think of the area interpretation, the signed area interpretation of the integral. The integral is the area under this piece of the graph minus the area above that piece of the graph. It's still going to be a positive quantity here because that area is bigger than that area. The average value still has to be positive. The average value is still, again, the height of this rectangle such that the area of the rectangle equals the integral of the red graph. But I didn't make this graph go down far enough and fast enough that eventually the average value is actually negative. So the area interpretation gets a little funny then. The integral is this area minus that area. in this case now, that area is bigger than this one. We're not seeing the whole graph, making the integral negative. The average value now is the height of this rectangle, but it's not the area of that rectangle that equals the integral, it's the opposite of the area, because the integral is negative in that case. You can actually think of this statistically too. Have you used random real in problem stats? Anybody in problem stats right now? Use random real. Random real produces a random real number. Well, is it truly random? Not really. It's only 6 decimal places. So it's not truly a random real number, but we go ahead and call it random real anyway because it's good enough. Every time you enter this, you get something different between 0 and 1. It should follow a uniform distribution. If you gathered enough data from random real, it should be uniformly distributed over the interval from 0 to 1. If I plug random real into the function, again, the function here is still the same one here, 2x squared minus x cubed. It's going to give me a random output between 0, not necessarily between 0 and 1, excuse me. A random output of the red graph, it will be between 0 and 1 in this case because the red graph is between 0 and 1 in outputs. But it will no longer be a uniform distribution because of the fact that the function f is not linear. Okay, so I mean, I am always going to get a number between 0 and 1 here. But it's not going to follow a uniform distribution because the red graph is not linear. If I let b go higher, say to the approximate location of the peak there, close enough to 1.3, then you do get outputs that are bigger than 1 sometimes. How can I sample such values with random real? I could multiply it by 1.3. 1.3 times random real now is going to be a uniformly distributed variable between 0 and 1.3. Sometimes I will get values that are close to 1.3, and I plug those into f, and I'm going to get outputs bigger than 1. Sometimes, not usually necessarily. There we go. There's one bigger than 1. The average value over this interval from 0 to approximately 1.3, let's just go ahead and pretend it is 1.3. Appears to be around 0.6. So if I gather a lot of data values statistically using random real and take their average, take their mean, I should get a number close to 1.6. So if I plug 1.3 times random real in here and take 100 data values, hopefully it's close to 0.6, is that what I said? 0.6. Not too far. Do 1,000 data values, it should be closer. Not much closer. What was the average value? From 0 to 1.3, it only looked like it was about 0.6 from the graph. It's actually about 0.577. So we are pretty close here. Let's try 10,000 data values. Yeah, we're pretty close to 0.577. So you can think of average value statistically. One more thing I want to say about average value. Well, I'm going to say 2 more things. We are going to talk about the mean value theorem for integrals, which is related to average value. But I think it's more useful, a more useful concept if you generalize it to higher dimensions, at least in terms of trying to understand or guess approximations to double integrals. Let's consider a function of 2 variables. Oh, how about x squared times y plus 3x times y minus y cubed. Actually, let's do plus. there's a function of two variables. Common application I think about when I do such a thing in multivariable calculus is to imagine this to be a density function of like a thin sheet of metal, maybe in grams per square centimeter. It's a thin sheet, so you can think about it as mass per unit area instead of mass per unit volume. And what you often do with such functions to graph them is you make a contour map. Remember that from multi? For example, I could make a contour map of this as x goes from, say, 0 to 2, and y goes from 0 to 2 as well. Add in lots of contours here. Maybe 50. There we go. Not straight lines, it's a nonlinear function. I could imagine this again being the density of some thin sheet of metal, shaped like a square in this case. What's the total mass? You have to do a double integral to help you do that. But if you want to try to guess the answer, the contour map can help you do that. And the concept of average value. The output is close to 0 down here. Over here, it's close to 26. Can you see that number there? That's 25.92 there. Real close to 26, 27, I guess, at the very tip there. Zoom in if you need to on that. That's a 27 up there. Pretty small. So the density of this thin sheet of metal in grams per square centimeter varies from 0 to 27. The average of the extremes, 0 and 27, would be 13.5. Is that the true average density? No, because it's nonlinear. It's increasing very rapidly up here because these level curves are close together. It's not changing so fast down here where the level curves are far too apart. And because of that, if you graph this in three-dimensional space, it would be like concave up this way. It spends most of its time, so to speak, in low values. In the majority of this region, the function's closer to lower values, closer to 0 than it is to 27. 13.5, in fact, you don't get to that value until you get up right about there, 13.5, to that level curve right there. So the average value of this function should be less than 13.5 is what I'm trying to say. It's hard to say exactly how much less. Dare I guess? Okay, this is just a guess. I'm going to guess. I'll give myself some wiggle room. Somewhere between 6 and 10. What does that mean about the mass? If the average density is somewhere between 6 and 10 grams per square centimeter, multiply that times the area, you're going to get a range of possibilities for the total mass. The average density is in grams per square centimeter. The area would be in square centimeters. Multiply those. Okay, I'm just saying this verbally. Maybe I should write something. Let's just pretend the average density is 8. I'm sure that's not right, okay? But hopefully it's not too far off. The average density happened to be 8 grams per square centimeter. If I multiply that times the area in square centimeters, which would be 2 times 2, 4 square centimeters, I would get 32 grams for the mass. 6 times 4 is 24, 10 times 4 is 40. I'm expecting a mass somewhere between 24 and 40 grams. If I do a double integral of this function, over this domain, hopefully it's between 24 and 40. I could be wrong. Hey, there we go. Just barely right. Okay, so the average density is closer to the lower end. It's closer to 6. In fact, the average density would be this number divided by 4, divided by the area. That would be the average value of a function in higher dimensions like this. Instead of taking 1 divided by the length of the interval, take 1 divided by the area of the domain, in this case a square, times the double integral of the function over the domain. That would be average value in higher dimensions. And the practical nature of it here is that it helps me guess the answer. Helps me know if the answer seems about right. You could do this over a triangle as well, by the way. A little review of multivariable calculus here when we do the double integral. I could add region function, arrow function. I don't expect you to remember this Mathematica code. Let's consider this over the triangle where x goes between 0 and 2 and y goes between 0 and, well, x. Then it's a triangle with area equal to 2 instead of 4, 1/2 base times height. What's the average density over the triangle? It's probably not too different from what it was before. And the graph wasn't perfectly symmetric in replacing x, swapping the nature of x and y. Yeah, okay, it should be different. It's not going to be the exact same average value, but it shouldn't be too far away, I'm guessing. Somewhere in the neighborhood of 6 or so for the average density over this triangle. So I'm guessing an answer about half as big as it was before because the area is half as big. To do the integral, you could do it this way. Ignore that q there. That would be one way to do the integral. As a vertically simple region, set in multivariable calculus. For any x between 0 and 2, like there, y goes between 0 and x. That's how to integrate over that triangle. I'm guessing this is going to be somewhere in the neighborhood of 12 or 13. A little less, that would be 10.8. So the average value is a bit lower over the triangle than it was over the whole square. That's the average value. I could call it V. I'm estimating the integral by estimating the average value and multiplying times the area. Multiply both sides of this by the area of D. That's helping me estimate the integral. That's what I'm doing. And in this case, the integral gives you the mass. There's a mean value theorem for integrals, and it's related to the concept of average value. MVT for integrals if f is continuous, essentially the conclusion is there is some c between a and b where f of c is the average value of the function. There exists a c between a and b such that in the equation for the average value, you can replace the v with f of c. There is a c where f of c equals the average value. There is a c where the height of the graph is the same as the height of the rectangle, whose area is the same as the area under the curve. The red graph does cross the blue graph. C in this picture would be right about there. There is a C such that f of c equals 1 over b minus a times the integral of f. Or f of c times b minus a equals the integral of f. Proof of this is not too hard, actually. Use the fundamental theorem of calculus. Let's just call it the idea of the proof. Let capital F of x be the integral from a to x of little f. We are assuming little f is continuous. Therefore, capital F is what? Differentiable. And its derivative is little f for all x in the interval. This is a mean value theorem for integrals. I wonder if I can prove it with the mean value theorem for derivatives applied to capital F. Mean value theorem from chapter 4 implies there exists a C between A and B. In fact, you can say it's in the open interval from A to B. Should also mean it's in the closed interval from A to B as well. Such that capital F prime of C is capital F of B minus capital F of A divided by B minus A. But capital F prime of C is little f of C. So to finish it off, I've got to simplify that. But that does equal the integral because of how capital F is defined. Capital F of B is the integral from A to B. Capital F of A is the integral from A to A, but the integral from A to A is 0. We're done. Follow that? Trying to apply the fundamental theorem of calculus, which is probably the best thing to guess you're going to need to do in chapter 5, even if you're not sure if it's going to work out. And you might wonder, it's a mean value theorem for integrals. I wonder if the mean value theorem for derivatives in chapter 4 would be helpful. So you try it, and amazingly enough, it works. That's the essence of the proof, is you just try what makes the most sense to try, and amazingly, it works out. Is it luck? No, it's not luck. It's a natural thing that follows from the truth of the fundamental theorem of calculus and the mean value theorem from chapter 4. Is it a trick? Not really. Again, it's like the only thing you could try. This is really more straightforward, even though you may not have thought of it on your own right away. It's the natural thing to try. There is this generalized mean value theorem for integrals as well. Even though it's got a name, you don't need to be able to write that on exam 3. You should be able to write the mean value theorem for integrals on exam 3. But we're not going to spend time with the generalized mean value theorem for integrals. Interesting that they use both the extreme value theorem and the intermediate value theorem to prove it, though, as well as the... Yeah, okay. That's interesting that they use those two theorems from chapter 3 to prove it. I'm going to talk about the rest of section 5.4 next time, about step functions. Okay? I am going to come back to that on Wednesday. We're going to skip it for now and skip ahead to chapter 6, because you're going to have a few graded problems for Wednesday that are going to be on chapter 6, so we're back to graded problems. What? You're glad that you got the break?
Yeah.
You'll get a break after exam 3 as well. The rest of the semester after exam 3 will be all completion. But it would be good, I think, for me to give you feedback on how you do with chapter 6 problems.
So we're just skipping 5.5.
We're going to skip section 5.5. I will come back to 5.4 some more on Wednesday. We're going to skip section 5.5 in numerical integration. By the way, we're skipping it in here, but you don't have to skip it in foundations of math. You could do study in numerical integration for your foundations of math paper in January, if that's something of interest to you. the content of section 5.5 could be your main focus for your paper, as one possibility. We're going to skip ahead to chapter 6 now, though. Infinite series, ultimately leading us in chapter 7 to consider Taylor series. Fun, right? You guys like that stuff? I like Taylor series more and more as years go by. I didn't like it so much at first either, but the more time goes by, the more I enjoy Taylor series. So I hope, if you didn't like it so much in Calc 2, that you'll like it more now. We will be doing some proofs, though there'll be plenty of computations as well. In fact, let's go ahead and start with the computation. Let's consider this infinite series here. Sum k goes from 1 to infinity of, let's make it 1 over k squared plus 7k plus 12. That doesn't look so pleasant. Is it possible to find this sum? Well, first of all, this is something I told my Calc 2 students last week, and I'm telling you now, and I don't know if your Calc 2 teacher told you. When we say infinite sum, or the more official name is infinite series, a little dirty little secret for future people too. There's nobody walking by. We're not actually adding up infinitely many things. Did you know that? Nobody can add up infinitely many things. Nobody. Okay? By definition, because it would not stop. We're only pretending to add up infinitely many things, and I'm being completely serious. But that pretending to add up infinitely many things can be made rigorous, okay? So we're not leaving rigor. We are going to rigorously define what we mean by this infinite series. But don't kid yourself into thinking we are literally adding up infinitely many things. Nobody can do such a thing. It's by definition impossible. I'm talking literally adding. Okay? But we can make this rigorous, what this will, quote unquote, sum to. And we can make it rigorous by referring to sequences and their limits. I'm going to call this thing A sub k. S1 is called the first partial sum, and it equals A sub 1, which in this case would be what? 1/20th. S2 is called the second partial sum. It's the sum of the first two terms. And these are literal sums. I am really adding here. No pretending there. 1/20th plus, plug in k equals 2, 4, plus 28 is 32, plus 12 is 44. 1/44th? Did I do that right? Oh, do I have to get a common denominator with these things? Okay, I could, I'm not going to bother. I can simplify it. S3, the third partial sum, is the sum of the first three terms. A1 plus A2 plus A3. 1/20th plus 1/44th plus, oh, plug in k equals 3 now. 9.
The second one should be 1 over 30.
What? Did I calculate it wrong in my head? Oh, I was thinking that was 7 times 4 in my head for some reason. No wonder people look confused.
We only count.
For some reason, okay, here's what I did. I did 2 squared is 4, and then I was thinking of the 4. 7 times 4. That's what I was doing in my head. Okay, 2 squared is 4 plus 14 is 18 plus 12 is 30. Mistakes forever on YouTube. Okay. When k is 3, I get 9 plus 21, right? Okay, okay. 9 plus 21 is 30, plus 12 is 42, etc. S sub n, the nth partial sum, would be the sum of the first n terms. No pretending there, that's actual summation. This list of numbers, S1, S2, S3, S4, etc., forever and ever, forms a sequence. It's called the sequence of partial sums. Does it converge or not? If it does converge, you say the series converges to the same thing. If it diverges, you say the series diverges. So you can make it rigorous. This pretending to add up infinitely many things can be made rigorous as to what it means. We pretend we add up infinitely many things and we get something convergent if this sequence of partial sums converges. And we even say the series equals whatever the limit of the sequence of partial sums is if it converges. Can it be found in this example? Can Sn be figured out? Yeah, it turns out it can be. You can use partial fractions to help you. AK is this, which after factoring is that, which can be written as A over K plus 3 plus B over K plus 4 for some A and B. Solve for A and B. Can I do it in my head here? Well, probably better not. Multiply both sides by K plus 3 times K plus 4, and you'll get this equation. You want this to be true no matter what K is. So a little trick is you can plug in special numbers for K like -3 and -4 to make it easy to solve for A and B. If you plug in K equals -3, that goes away, this becomes 1, A must be 1. And if you plug in K equals -4, this goes away. That becomes -1 times B. B must be -1. So, because of that, you can write the summation like this. And this is a partial sum here. The upper thing there is not an infinity, it's an n. When K is 1, this is 1/4 minus 1/5. When K is 2, it's 1/5 minus 1/6. When K is 3, it's 1/6 minus 1/7. The last couple terms, when K is n minus 1, it would be 1 over K plus 2 minus 1 over K plus 3. And when K is n, well, it's supposed to be an n there, sorry. When K is n, it's 1 over n plus 3 minus 1 over n plus 4. I hope you see right away that a bunch of stuff cancels. It's called a telescoping sum. Maybe it's because, I don't know why they use the word telescoping, like we're zooming or something, because a bunch of stuff cancels, goes away. It's like you're looking under a microscope or something. I don't know why the analogy is the way it is, etc. This cancels with that. This cancels with something back there. The only two things that don't cancel are the 1/4 and this. The nth partial sum equals 1/4 minus 1 over n plus 4. That is a formula for Sn in general. As n goes to infinity, that has a limit, 1/4. So we say the infinite series converges to 1/4. We even write it equals 1/4, though that equals is a little bit suspect in a way. It seems to imply that we're adding up many things, but we're not. We're only pretending to. that pretending is not only maybe beneficial for intuition, it does help you apply it in physics, for example. That pretending to adequately define things can be helpful. Mathematica will do the pretending here as well. I'm going to put an infinity up there. 1 over k squared plus 7k plus 12 1/4. So this infinite series converges because the sequence of partial sums converges. Since the sequence of partial sums converges to 1/4, we say the series converges to 1/4, and we even write that the series equals 1/4. We can even abuse notation, you might say, to say it equals 1/4. Not what I circled there, but the whole thing equals 1/4. Make sure you pay careful attention to distinguish between the terms we are adding, which themselves form a sequence, and the sequence of partial sums itself. They are related, but they're not the same thing. To have any chance for the series to converge, the a's must converge to 0. However, the a's converging to 0 does not guarantee convergence, and the most famous example is the harmonic series. That series has terms which go to 0, but the series itself diverges. Even though you're adding up terms that get closer and closer to 0. Okay, that series diverges. It's called the harmonic series. Let me end class today by just showing you something kind of interesting. I may have showed you this earlier in the semester. You might think that this series would be easier to prove convergence for and find the value for than this one. It's simpler looking after all. But actually it took a genius, it took Euler to figure it out. It does converge, but it converges to something unexpected. Pi squared over 6. Did I show that to you? Okay, I showed it to you earlier in the semester. And in fact, yeah, I think I also showed you that if you plug in any even number for that power of the k, it converges to a rational multiple of pi to that power. Euler's methods can be generalized. Though if you plug in an odd number, like 3, there is no such simple expression for the value of this series in terms of pi cubed. It's got a name though, it's called zeta of 3, referring to something called the Riemann zeta function, which is related to the Riemann hypothesis. I think I mentioned this first or second day of class, which is the most famous unsolved problem in math. Okay, if you solve the Riemann hypothesis, you'd be famous, you get $1 million, there's a prize, $1 million prize for solving it. Don't kid yourself though, you have to have really advanced math classes before you can have a chance of solving it. Okay. If you look up the statement of the Riemann hypothesis, it sounds really weird. And you scratch your head and say, why is this the most famous unsolved problem in math? Because it's just weird. It sounds useless, but it's related actually to distributions of prime numbers, which is related to cryptography, which is related to keeping your internet transactions secure, at least until somebody develops a quantum computer. I'm serious about all this, okay? Not an expert, but that's my understanding of everything. At least until somebody develops a quantum computer, your internet transactions are secure, because the Riemann hypothesis, though it's not proved to be true, does seem to be true, is the idea. Nobody's disproved it, and it seems like it's true, just nobody's rigorously proved it.
So one day, are we just going to have to go back to using cash?
Yeah, and I think the government is going back to using handwritten notes now with all this email stuff that's going on here.
Well, I'm sure.
Yeah.
Can't trust no one.
Handwritten notes. Okay, we'll see you. Have a good day.